Good day to you. This is Anagalactic. On the 4th day of October, we have a consolidated sequence ahead, which requires just a tiny bit of annotating, because in the production sequence, you'll hear the term kinetics. You'll see I have a Wikipedia article highlighted, classical mechanics, kinetics, mechanics, and dynamics. These are not exactly the same thing. Now I need to just make sure that we all are on the same page when I use the term two-force kinetics, referring to Ruđer Bošković's work. This now rising to the top echelons of physics because it's miraculous. So that's what we'll be talking about today. It is a branch of classical mechanics, there's our word, that is concerned with the relationship between the motion and its causes, specifically forces and torques. And since the mid-20th century, the term dynamics, or analytical dynamics, has largely superseded kinetics. So dynamics is the modern term for kinetics. How does kinetics have anything to do with Bošković? It's that two-force kinetic system that I refer to in our sequence today. You see that it refers to a book which I own. Actually, I have 2 copies of it. Bošković's work and its significance in physics today. This is quite real. This is the only reference in the article on Boscovich in Wikipedia that refers to, it doesn't really say what he did. Well, that's because nobody knows what he did. So that's what we're going to be talking about, is what Bošković actually did, but this is the only reference to what he did. Is right here where it says his atomic theory and his theory of forces. So that does make definite reference to Bošković's work, but in just a fragment of a sentence. Well, we're going to go on here and look at something else for completion. This, you may recognize, is your dear professor without his hat and glasses and wearing a tie for a change. Because I'm making a formal presentation, I'll have a link to this so you could watch it if you want. You can see it's about an hour long. And it's about forces in Bošković's theory, which is by a man named J Anderton. And if you're interested in Bošković's work, which you should be, all of his stuff, and he's out on YouTube as well. Dragoslav Stoiljkovic is Croatian, as was Ruđer. He got involved, and he's out trying to promote Bošković's work because it's very important for physics. It's unknown, you understand, so you're at the cutting edge now of the future. You're actually ahead of the game. This was to introduce our republication of differential calculus. Stop recording. We'll be back with interjections throughout this production. Good day to you. This is Anagalactic on the 14th day of July. Two-force kinetics is a mechanical system for physics. That was invented and discovered by Ruđer Bošković. So curvature is nonlinear continuity, based in two-force kinetics. The two-force kinetic system of nonlinear continuity, which we call the circle, might be plus-minus polarized. That's the definition of electrodynamics. We're going to find out that that is quite naive. Do you know the relation of space to time geometrically? They're orthogonal. Does that make sense? Yes and no. It's a perpendicular relationship. Now what he did is use the existing 3D grid in order to extend it to 4D. And what he got then was a cubic solution with an extra degree of freedom. That allowed him to complexify 3D space. That's what he did by introducing time as an orthogonal imaginary line. Since it's imaginary, you now have hypercomplex space. This is known, it's in a somewhat esoteric form. So Einstein induced a cubic solution, which is then called space-time. It's because of the extra degree of freedom in 4D. Minkowski discovered that. Einstein got the hypercalculus to give it a mathematic formula, which works to a threshold or we would not have space travel. Now, dynamically, Space is actually perpendicular to energy, but you do have to understand continuity as being the inherent functionality of a closed line, which is a circle. That induces a notion of continuity, which of course the universe is continuous. It's not quantized anywhere. The quantum jump is an illusion. It's an artifact of linear mathematics. This is a more direct route to seeing the entire synthesis. So I hope this is helping you thus far. It's incredibly deep. Nobody ever probes this way. But there's nothing really mysterious. It's just a matter of insight. It doesn't mean that the discoverer will get the right answer. Einstein proved that. Because we're always getting to a new threshold. That's all we can do, because we're finite. So the actual relationship is not space is perpendicular to time. It's space is perpendicular to energy. And in order to find out where time is, because Einstein used time, so it has to be real in some sense. It is. Time is real in a derivative sense with respect to energy. Energy is frequency proportion wavelength. Linear frequency from linear wavelength is proportionality. That's a fraction. It's a fraction, but it's not division. We're accustomed to saying that a fraction implies division. A fraction is a proportion. 1 over 2 is the relationship of 1 to 2. It's a relationship of 1 to 2. It's not 2 divided into 1. It's the relationship of 1 to 2. If you invert that, it's the relationship of 2 to 1. And we know what to do with that. We reduce it to a linear number 2. Don't do that. Don't ever do that until the last step. It's the same as when using complex numbers. You never reduce the complex numbers to their linear components. You use them in place as complex numbers until the last step. And then you have a complex solution. Then you have to translate it. That's always the last step of a complex number calculation. You get your complex solution in complex space. And then you use the translator, which you've proved is consistent, to translate the complex number, which is one number, into two linear numbers. That's the nature of the complex plane. This is the proportional plane, which leaves behind the complex plane. We'll never need it again because the proportional plane is more real. All right, let's go on. Spatial space is already composed for Einstein, and he simply had it handed to him on a silver platter. Here is your cubic space, Albert. See what you can do with it. Well, he took 3D space, which is linearized space, so it's already been linearized for him. So Einstein got a finished product, linearized spherical space, because he was dealing with a spherical phenomenon called gravity. That is nonlinear. That's spherical. So you need a spherical number system just to express it. Einstein could not figure that out. Nobody had been able to figure that out. Nobody ever would figure it out until I figured it out. So Albert used derivative space. The 3D cubic system for coordinating space, that is, giving it a coordinate system, is the derivative solution. It's the derivative systematic space of one component numbers. You use three one component numbers to parameterize spherical space, which is inherently a two component number. So you're really splitting when you use a spherical geometry, which is the definition of gravity, is a spherical system. It has a center. the center of gravity, that means that the whole thing is spherical, which we already know. But that's not linear. So here's the nature of the nightmare that we've inherited from Albert Einstein, who is not really to be blamed. Or if you want to blame Albert, blame him for not figuring out what I just figured out. That would have saved a lot of agony. It's too late now. What we actually do in physics, everywhere, is we take a linearized spatial space, which is a derivative system because you're using lines which are derivative objects. I proved that in 2022. So 3D space is already wrong. It cannot possibly serve as an analytical tool for spherical space because there's no match. You're taking a three-dimensional system, which means three lines, and you're getting positions in that cubic space which are inherently two-component numbers. And so you're trying to get three numbers out of one number, which is already a two-component number. That's a nightmare. That's an error. It's an error to use 3D space. Well, up until today, we thought we've had no choice. In a sense, you could say that, but I've discovered the secret way around that, which is lying right in plain view the whole time, so let's go on. So the actual relationship is not linear time, which is 1D. That's ridiculous, because time is not real. It's not physically real. Time is derivative. So if you're going to say it's real, you must say it that way. It's a derivative reality. If you want to think of time as being one-dimensional, you can do so. How do I know that? Einstein did. He treated time as if it were a one-dimensional space. And by doing so, he used a linear derivative of energy. That's what time is. It's one of the two linear derivatives of energy, because energy has two components, frequency and wavelength. Both of those exist on a closed line. Correct? Of course that's correct. So it's not linear time unless you call it frequency. And on a sine wave, you can then measure this circular component of energy, which is the fractional component on the circle. That's frequency. Frequency is a temporal term, not a spatial term. But wavelength uses the word length. And that is the spatial component in circular space. So you have a frequency component, which is the temporal component of energy, and the spatial component of energy, but both of them are nonlinear. So frequency is nonlinear, but you could treat it as linear, can't you? Well, you have to if you want a number for it, a computable number. So energy is not a computable number, but the two components are. You can break energy down into frequency and wavelength. Well, that's what Maxwell and Planck did. This is frequency proportion wavelength, which is a fraction, but it's a spherical relationship. This whole thing can be composed with a spheric right angle, which I discovered. Boscovich showed the right angle exists at the quantum scale. There is a quantum right angle. I discovered that the quantum right angle is a spherical right angle. Boscovich got it. He got the algebraic answer for what happens when two particles collide. That's been a mystery for centuries. It still is a mystery, and the cyclotrons are unable to break this mystery. I have the geometry to substantiate Boscovich's insight. It is a right angle, essentially between energy and space. The protons, when they are forced together with a little bit extra velocity to overcome the repulsive force, and they get close enough to each other, they bind. So the valence of the force field inverts. That means there are two forces. All right, so he showed that the proton-electron force curve at the inner binding radius, which is fixed and constant, we know that, as only the inner shell of a multi-shell geometry we now call the atom. Boscovich figured that out, that it has to be a shell system. Here we begin an often overlooked relationship between numbers. In linear dimensionality, Euclid taught us that you have to start with a 0th dimension. Otherwise, you can't define a point. But once you do define a point as being null, you can use that nullity to cut off one end of a line segment. From that, you can get 1D, a line segment. 2D represents two lines that are orthogonal. 3D adds the third orthogonal line to fill volume space. And the fourth line has to be imaginary because it's not spatial. Einstein assigned time to that dimension. That works, but we're not going to say why. Here is the right solution, where you do not begin with 0 as Euclid did. Instead, you begin with 1. And 1, instead of splitting into plus and minus, these, by the way, are the positive dimensions. You can see that that can be reversed and go back this way. If you extended it with arrows pointing, it would be negative. That's actually been utilized, only very strangely, in the complex number system, which is based on the square root of -1. That does not work. This does work. It's relative when I say it works or doesn't work. This does not work for anything in physics. It only works for spatial separation, for linear spatial separation. But once you introduce the time component, you've inadvertently introduced motion. This two-number component system, this is a component, and this is a component, and this is the center of the system. Here, this is the center of the system, and these are the positive components, but they're balanced on the negative components. Here, it's power space. The 2 plus refers to 2 to the first power. This refers to 2 to the negative first power. These two numbers multiply to 1. That is the original number system. This is the calculus derivative number system. This will all make sense. The composition of universal space can be accomplished on this system, where you use the negative power of infinity to the positive power. This is spherical infinity, and these will multiply to 1. The dynamic system of proton-electron space that we call the atom is founded on a perpendicularity between the two infinities of natural space. This defines the universe. This defines the quantum. Light speed, therefore, cannot be constant. The reason light speed cannot be constant is because it's this number 1. But you see, that oneness, that unity, is based on a balance between this number and this number. So light speed is a composition of 1 over 2 and 2 over 1. That's the simplest frequency. The lowest frequency is 2. That's been proved. Therefore, the lowest wavelength is 1/2. That is the Planck length. The Planck length is the measure of that. So light speed cannot be constant. If light speed were constant, then it would mean it could never change speed. But it does change speed when it's emitted and when it's recovered. The question that's been brought up by Alexander Unziker, based on a 1911 insight of Albert Einstein is that Einstein first conceived of light speed as having varying speed, but not just in the way I just said. Rather, when it's in free flight through space, it cannot have a constant velocity because of gravity. And the reason for that is so profound that no one understands it. They say it without understanding it. Which is what? What we say is that light speed is constant in free space, but which is often called vacuum space, which is a contradiction. The insight of Einstein, which is overlooked, is that the reason that why light cannot have a constant speed, the photon cannot have a constant speed in free space, because space is curved. We measure the speed of light on a straight line. How is space curved? Spherically. And so time is expressed as a derivative of centrifugal energy. There are two energies. One is centripetal and affects space. One is centrifugal and has no effect on space, but is directly affected by space. That's the correct relation between space and time. It's the relationship of a derivative number of centrifugal energy. Gravity, as we conceive it on a straight line of gravity, is the derivative of spherical gravity. So space is expressed in centripetal energy as the force field curvature. In 2022-3, Anagalactic showed that the Boscovich force curve for both the proton-electron relationship and the proton-to-proton relations define both quantum orthospheric interactions and solving the ancient twin paradoxes of impenetrability and continuity. The definition of calculus. This is critical, and we're going to end on this. We begin with the differential calculus. Differential or integral. When we go to define calculus, we mean the differential. We must never refer to integral calculus because that is a different tool that does a different task. Integral calculus is not the calculus. You could say that it is, we will later, but for now, no. Calculus is always introduced on this false note. Takeaway: fuck the integral. Fuck the integral. We need to understand the derivative. This fact proves that teachers never understand the calculus, and because those teachers don't understand it, they cannot teach it. So the very first thing that you must know walking in is that the calculus must be constrained to the differential calculus. That is inviolable. To learn it. So what is the differential calculus now that we've disambiguated the word calculus? It is a tool with extensions. What we want to understand is the fucking tool, not its extensions. Why has not science adapted to this new tool? It cannot be taught right, so obviously no one understands it. The main reason no one can understand the tool or its proper use is that the geometric basis for understanding the tool is ignored, bypassed, and forgotten. That is a problem indeed. So no one teaches real calculus. I will. This implies that we ourselves must discover the true meaning, purpose, and use of the tool. To do so, geometry is the only key. Remember that. Geometry is the key. So what is the geometry of the derivative? The nomenclature investing the tool, even as we have defined it so far, is still indicative of psychosis. First of all, we must deal only with the differential. You might say it's differential calculus, or the diff calc. You don't need to worry about that. The first signal that we've entered the Hatter's Tea Party is the instant bifurcation of terms. That means a split in meaning. The differential is also called the derivative. Why use two terms for the same operation?
Close as you like, as precise as you like, as close
as you please.
As you please? Isn't this supposed to be mathematics?
No, this is not mathematics. First of all, differentiation is a process to get a derivative. However, the word derivative implies a process, derivation. Thus, the first rule is to restrict the definition to the differentiation of the derivative. Then a second rule should be applied. Never to use the process term, but always to refer directly to the derivative. If you want the verbal form, it is to take a derivative, not to differentiate. That's a useless extra baggage term. You take a derivative in order to get the derivative. Now that we have correctly defined the term calculus, we are now prepared to study the process of taking a derivative. What the F is a derivative? The derivative, the object of calculus in our first stage approach, is irrational. Why? And why would that matter? To answer this question, we require a rigorous definition of the domain of input. That's somewhat redundant. What is it that we are computing? The way to express this process of computation is by defining the domain and the range. Okay, everyone knows that, but I don't think you've ever heard it explained so realistically. Why do we have these terms domain and range? The domain is the input, the range is the output. Each of these, the domain and the range, refers to a data type. A data type, which can be constructed as one word. First, we want to talk about the input, which is the domain. The goal of the calculus, as with all numeric operations, is to make numbers produce other numbers. All numbers have a data type. So the first task at hand, in order to understand the calculus, is to distinguish the domain of numbers used to substitute into the variables of the calculus formulae. Once we know what types of numbers go into the equation, sometimes the text gets a little raspy. The technical definition, let me go back. All numbers have a data type. Once we know what types of numbers go into the equation, we can analyze the type of the resultant number. This is the hardest part in understanding the calculus, is the difference between the domain data types, or data type, and the range data type. The reason this whole process is couched in mystery can be stated, at least in one way, as the mystery of irrationality. That is actually the correct way to approach it, but that needs explanation. Let's go on. In numerics, or what we call mathematics, all numbers can be classed according to a simple initial rule. A number is either rational or irrational. There is a technical definition of numeric rationality worth knowing, even though we shall apply it in a slightly improved form. The technical definition of a rational number is that it is a two-component number written in fractional form, such that it can be reduced to a one-component computable number. Although this is the precisely correct definition, this definition remains unused, avoided, and shunned. And the reason for that leads down another rabbit hole into Alice's fucked-up kingdom. We wish to avoid that hole. The plain fact is that there is a persistent misapprehension of what is a computable number. By the way, one of the foremost geometers left on Earth who's still kicking, he's in Australia. His name is Norman John Wildberger, one of my teachers. To be rational, the number must be computable, which means computer representable, technically binary representable. This fact has relevance in our considerations at hand because we are now able to give a concrete example of domain and range in algebraic computations. In this case, the domain is always two numbers, right? 2 and 1 would make 2 over 1, or you could use 2 and 1 to make 1 over 2. And those are the only two ways to compose those two numbers together to make a fraction. That's a relation 1 to 2 or 2 to 1. That's elementary. In this case, the domain is always two numbers, whereas the range is one number. That is a critical insight in your understanding of the calculus. You're trying to take two numbers and turn them into one number. So in the process, the simple process of fraction reduction, the numerator and denominator, are computed together to produce one number. The fraction is not one number. That's what's persistently denied. A fraction is not a number, you might say. Well, is it or isn't it? You have to be more specific. However, that's not really correct. The fraction is a number. A fraction is a number, but what kind of number? That's the lacuna. That means a hole in your head. The proper way to say this is that a fraction is not a one-component number. As I've been able to prove, a fraction must be called a two-component number. That is tautological. Well, that's the kind of number derived. You derive a two-component number, and then you pretend that it's a one-component number. That's calculus. Thus, the range of the calculus is a two-component derivative. That is, the output of the calculus is a two-component derivative. All of this critical insight is obfuscated in every course in calculus. That's what makes it a nightmare. Well, that's the first step in the nightmare. You are trying to relate two numbers. You are trying to relate two numbers into a two-component number. Two linear numbers into a two-component, a different data type. This is called the derivative number. It's a different data type. It's expressed as a rate. That's very important. Just file that for now. This term rate is profoundly new as it has defined two-componency. That is, rate defines two-componency. Two-componency is the data type of rate. In a useful way, a rate is a derived number. It's not a linear number. The objective is to linearize it as closely as possible to a linear number. This cannot be done. That is called the barrier of irrationality. The key to the calculus is to ignore the law. You do it anyway because you want to. And you're going to do it even though nature says you can't. That's hazardous, as we have found out. You cannot ignore a universal law without a severe penalty. That penalty is felt throughout physics. It's because of the calculus. It is being felt today directly in two prominent arenas, one of which concerns the differential, whereas the other concerns the integral. We haven't gotten there yet. Both of these, of course, are numbers. That is, the integral is a number, the differential is a number. But what kind of numbers are these? Two-componency numbers. This diagram also shows the secret of spacetime and the role of energy, primarily the two-force dynamical system, which explains everything from the atom to gravitational systems. We have the answer, and I am applying it. Thank you so much for tuning in. Stay tuned and keep looking up. We'll be right back with the best.